Alright, so in this section we're going to discuss another implication of Faraday's law. So we're going to start with a solenoid. And we are going to vary the current in the solenoid. So we know that the magnetic field strength of the solenoid is equal to the magnetic constant times the current times the number of loops divided by the length of the solenoid. So we derived that using Ampere's law in an earlier example problem. That means the magnetic flux through the solenoid is going to equal the magnetic field strength times the area. Now, in order to have a change in magnetic flux with respect to time, as I said, we're going to vary the current. So all of these up front here are going to be constants, and what we're going to vary is the current. And I'm using little I because little variables are going to represent things that vary with time. Alright, so this is going to be the source of our change in magnetic flux. We're varying the magnetic field strength through the solenoid. Now we're going to put a loop through the solenoid. And what we would observe is as we change the flux through the solenoid, it's going to induce an EMF in that coil. And we're going to be able to calculate that induced EMF using Faraday's law. So it's going to relate to the change in current in the solenoid. Now, so far this doesn't seem that strange, but what is different here is what is actually causing those charges in the loop to actually move. When we did our prior section where we had motional electromagnetic force, the metal bar was in the magnetic field, so we could easily use our right-hand rule in order to see the direction that the charges were going to move. But here, the loop is not actually in the magnetic field. Remember, the magnetic field goes through the center of the solenoid. So this is where our magnetic field, at least the intensity of that magnetic field strength, is going to be. So the loop isn't actually in the field. So we have to wonder what is actually causing that induced EMF. And that's going to turn out to be actually an electric force. So it turns out that changing the magnetic flux actually causes an electric field. So we have to pull out our dreaded equation that the EMF is equal to the integral of the electric field dotted with dl. So the induced EMF leads to an electric field in this loop, which causes an electric force, which actually pushes the electrons around. So our path dl here, for this case, would be the path or the circumference of the circle. So another way of stating Faraday's law is to say that the integral of the electric field dotted with the path is going to equal the change in magnetic flux with respect to the time. Now, what is odd about this situation is that when we applied Kirchhoff's law earlier in the semester, we essentially stated around the path that the EMF had to equal 0. So as we went from one point back to around to the path, the EMF had to go to 0. And that should make sense because we have to remember that the change in potential is equal to work per unit charge. So if we say the electric force is a conservative force, we expect it to be path independent, or that when you return back to your original position, the work done is 0. the situation we're in now, which we refer to as a non-electrostatic situation, we find out that the electric force is not conservative. So electrostatic and non-electrostatic, the electric force behaves differently.